Hello everybody, my name is Chris Brady, author of the Boeing 737 Tech Guide and the Boeing 737 Tech Site. And this presentation is covering electrical power part 2, DC, standby and the circuit breakers. So covering DC and the standby electrical power system on all models of the 737, but with particular focus as usual on the NG and the MAX series. In this case with dual battery configuration. As usual, please always treat your company training and their manuals as the authoritative source of information. So I'm going to be looking at the DC system, the TRUs, batteries, standby system, faults and diagnostics, and circuit breakers. Right, this is the electrical schematic, which hopefully you've seen the AC presentation first before coming to this one. If so, you'll be familiar with that. AC is everything above the red dotted line going through the TRUs. DC is pretty much everything below that line. Standby, as you can see, the bottom left corner. So in this presentation we'll be covering the DC and the standby, everything below the line. Starting with the sources of DC power, the first common misconception to folk new to perhaps airliner systems or maybe new on type, some folk tend to think that the primary source of DC power are the batteries. In actual fact, that's not the case. They don't have the capacity for that. The normal source of DC power are the TRUs, and there are 3 of these transformer rectifier units on the 737, and they are in turn powered from the AC transfer buses, which are of course powered in turn from the generators. The batteries are backup power sources of DC power. So if by any chance you've lost all AC generation, so that would have to be both engine generators and the APU, and you're down to battery power, then you've got the batteries as backup sources of DC power. Most 737 NGs and MAX are the dual battery config, so they've got a main battery and an auxiliary battery. Okay, so let's take a look at these transformer rectifier units. The photo on the right is one of those. There are 3 of these, as I've said, and they live in the E&E bay. Their job is to convert 115 volts AC into 28 volt DC for the DC buses and the battery bus. The check for TR serviceability, if you're looking on the meters, is current, not voltage, because the TR voltage simply indicates that of the associated DC buses, or at least that's the case for TRs 1 and 2. Each TRU has a supply capacity of 50 amps on the classics and 75 amps on the NG and the MAX when cooling air is available. Of course, cooling air is available with the equipment fans. The TRs are unregulated, so therefore they have a voltage range, and that's between about 24 and 30 volts. The TRUs are themselves powered from the respective transfer buses. So TR1 is powered from AC transfer bus 1 and TR2 from AC transfer bus 2. And as I said, the transfer buses are of course powered by the generators. On the NG and the MAX, which is the schematic I'm using throughout these presentations, TR3 is normally powered by transfer bus 2. But if that should fail or become depowered, then it's backed up by transfer bus 1 via the TR3 transfer relay. On classics, the TR3 is only powered by main bus 2. Don't forget, on classics, main bus is the equivalent of the AC transfer bus on the NGs. Okay, so onto the various DC buses. Starting with the DC buses themselves, they are powered by TRs 1 and 2, backed up by TR3. And these are used for things like VHF 2 and 3, spar valves, the flight control computers, engine anti-ice. That's engine anti-ice actuation. Obviously the anti-ice itself is hot air pneumatic. The first officer's displays, windshield wipers, etc. In my book, there's a huge, extensive list of every service from every bus, but to give you a flavour of what they're like, I've given you those examples now. Now TR3, its primary function is to power the battery bus, so it's a dedicated TR unit for the battery bus, but it does have a secondary function which is to back up TR2, as you see on the schematic. The DC crossbus tie relay, now that is, with the transfer bus switch in auto, the DC crossbus tie relay is normally closed. So effectively TRs 1 and 2 are working in parallel to power the DC buses. So with this DC bus tie relay, DC bus 1 and 2 are connected. But when with the switch still in auto, the DC bus cross tie relay, it opens automatically a glide slope capture during either a flight director or an autopilot coupled ILS approach, and that's to isolate DC buses 1 from DC bus 2 to prevent a single failure from pulling down both nav receivers and flight control computers. The other function, I guess, of the bus transfer switch is the off position. Should you ever choose to put it there, that will manually open the DC bus tie relay, amongst other things. But I will come on to the other functions of the bus transfer switch later. So TRU failures on the NG, failures of TR1 or TR2 and 3 are monitored by the TR unit light, as shown on the right. On the classics, we don't have these lights on the metering panel, so you have to check TR1 manually by selecting TR1 on the left hand side there and checking the meters. Obviously on the classic in particular, it's good practice to check these, to check TR1 before committing yourself to an auto land, because as we've already seen, that a glide slope capture, the cross bus tie relay will open, and that will leave DC bus 1 unpowered if the TR1 had previously failed. I say on the NG and the Max, you don't have to physically check, because the master caution system will alert you to the TR unit light illuminating. One slight difference between the airborne and the ground case for the TR unit light is that the TR unit light will illuminate if any of the TRs fail on the ground, whereas in flight it's 1 or 2 and 3 together. Okay, so more about the bus transfer switch, which I mentioned earlier. It not only controls the DC bus tie relay, but also the TR3 transfer relay and the bus tie breakers. So if you were to put the bus transfer switch off, it would absolutely separate the left and right hand sides of the electrics, both AC and DC. In the auto position, the bus tie bars, the TR3 transfer relay, and the DC bus tie relay all work automatically as necessary. And by automatically, what we mean is, well, starting from the bottom though, the DC bus tie relay, that is normally closed. So there's normally a connection between the two sides of the DC, unless a glide slope capture, in which case it opens. The TR3 transfer relay is normally in the position shown there, so we've got AC transfer bus 2 powering TR3. If you lose power to AC transfer bus 2, the relay will move to the other side and TR3 will be powered by transfer bus 1. And the bus tie bar relays work in whatever combination is required so that there's no paralleling of AC power sources to the transfer bus 1 or 2. That is one of the golden rules of AC electrics, which you remember from the previous presentation. I'll say in the off position, DC bus tie relay will open, TR3 will switch across to transfer bus 1 side, and the bus tie bars will open unless needed to be closed to power the respective transfer bus. And the only situation that would happen, well, the only in-flight case would be if you're down to one engine generator and you need the APU Jenny to power one of the buses. Okay, so that's the bus transfer switch covered. The battery bus, as you can see, is normally powered by TR3. The alternate power supply, so if TR3 is itself not being powered, the alternate source of power for that is the main battery or the battery charger. Now, the battery bus is used for engine controls, oxygen controls, fire detection, generator disconnection, manual pressurization control, pack valves, master caution annunciations, standby compass light, etc., etc. Again, an exhaustive list of these is in the book. But you can see it's all pretty important stuff, which is why it's backed up by the battery. The switched hot battery bus, as the name would suggest, is only powered when the battery switch is on. This is normally powered by the battery or the battery charger, and this is used for the ADIU, APU control, Genibus PCU, etc. Those sort of things. So a higher level of importance. The hot battery bus is always live. It's normally powered by the battery or the battery charger, and the alternate power, so if there's no AC, is the auxiliary battery. When ground power is supplying the aircraft, then the ground service bus will supply. And this is used for fire extinguishing, the clock, parking brake, fuel shut-off valves, the vac signal, etc. So this is the ultimate level of importance. Now I've mentioned and sort of glossed over before this slide that the battery or the battery charger supplying the hot battery bus, switched hot battery bus, and the like. If we think of the main battery charger as effectively another TR, probably the best way to think of it is TR4, although it's not labelled as such. The battery charger, as you can see, it's powered by the ground service bus, which is in turn powered by transfer bus 2, and obviously in turn by a Jenny. So if there is AC power to the aircraft, the main battery charger will be powered. And what it does is it charges the main battery, of course, as the name suggests. But once the main battery has been charged, once that charging is complete, then the main battery charger then charges the switched hot battery bus and the hot battery bus and the standby system if necessary. So it as you say, the battery charger is much more than a battery charger. It is another TR. The batteries, they're 20 cell 240 volt NiCads located in the E&E bay. This photo here is of one of the aircraft batteries in a Classic. We know that because it's on a DC external power receptacle at the bottom there. So you can plug in an external source of DC. Yes, you could jumpstart this off a 24 volt source. You plug into the receptacle there, and from there you can start the APU, which will power the battery chargers. On the NG and the Max, they decided this wasn't a good idea. They took away the DC power receptacle, and they decreed that if the battery voltage ever became so low that the battery needed charging, it must be replaced. So the DC power receptacle is now a thing of the past. The photo here up on the top right there, that shows the arrangement in an NG. That's actually a dual battery installation. You can just about count the cells there and see that there are two batteries. The one at the front is the auxiliary battery, and the one at the back is the main battery. So, battery ratings. The battery has been upgraded many times in the aircraft's history, and on the table you can see how the ratings have improved over the years. Back in the beginning, on the originals, the rating was 22 ampere hours, which gave you a standby power time of just 20 minutes. That was later increased to 30 with later originals. The Classics had anywhere between 36 and 40 ampere hour batteries, which gave a standby power time of 30 minutes with a single battery, or 45 with the APU battery. NGs, you may have 36 or 48 AH batteries fitted, which give you either 30 or 60 minutes standby time, and the Max have all got a standard 48 ampere hour battery, which gives you 60 minutes of standby power time. So a lot better, 3 times as good as the original 737-1 and 200s. So a bit more about the dual batteries. On the Classics, it was known as the APU battery. These weren't particularly common. I flew them a few times on a 500 fleet I used to fly. The APU battery, as the name would suggest, is primarily used for starting the APU, but it will also work in parallel with the main battery when you're on standby power, to increase the standby power to 45 minutes. And one of the big bonuses with this, if you had an APU battery, if you were to lose all AC generators, then you would keep power on the captain's EFIS. So that was a very welcome addition. The NG and the Max have what's called an auxiliary battery. Now this is like the APU battery. This is normally isolated unless the main battery is powering the standby system, when it then works in parallel with the main battery. The auxiliary with the main will give you a total of 60 minutes of standby power. Now, it may surprise you to know that there are actually a couple of other batteries on the aircraft. This one shown in the image on the right there, that is the battery for the ISFD, the Standby Artificial Horizon. This is actually a combined battery charger and a battery. Again, I've spoken before of the importance of battery chargers. So once the ISFD battery is charged by the battery charger, then it effectively works like it powers the ISFD directly, thereby preserving the life of the ISFD battery. This unit is housed in the E&E bay. and if it should lose power, the battery's got 150 minute capacity, so that will certainly get you home. So this battery charge is powered by the battery bus, which in turn charged by the TR3, or the main battery is the alternate power source for that. When the battery switches off, the battery charger removes power to the ISFD. The other hidden battery is the fuel shutoff valve battery. So this is only on the NG and the Max. It's an extra dedicated battery to be able to close the APU and engine fuel spar shutoff valves. Obviously, it's only fuel spar shutoff valve in the engines, but it also enables you to shut off the fuel to the APU as well. And this also is a combined charger and a battery, and it's actually housed there behind the P6 panel. This is powered by DC bus 2, which is in turn powered by TR2, which of course, as we know, is backed up by TR1. There are optional battery overheat and indeed APU battery overheat lights on the Classics. You can see them there on the aft overhead panel. If one of these should illuminate, there is no crew action required, other than of course to put it in the tech log when you get down. Battery discharge light is probably a bit more eye-catching. On the NG and the Max series, these are found on the metering panel, and they will illuminate if the current draw is more than 5 amps for 95 seconds, or 15 for 2.5, or 100 amps for 1.2 seconds. The only time you routinely see this light on will be during an APU start without ground power, and that's what this photograph is. And you can see it's pulling nearly 400 amps there to start the APU. On the Max, in addition to getting the discharge light, the ground crew call horn will sound a continuous tone 2 minutes after a battery discharge condition is detected. Obviously 2 minutes is longer than the length of time it takes to start an APU, so it won't sound, that's probably why they pitched it at 2 minutes rather than anything shorter, where you might get nuisance alerts for every time you light the APU. Alright, so that's the DC system covered. Let's have a look at the standby system now. Now this is for essential AC and DC loads. The power, when powered from the batteries, it's guaranteed, as we've already said, for 30 minutes on single battery aircraft or 60 minutes on dual battery aircraft. The point I want to make here, again for newbies onto the 7.3 or for folk new to airliner electrics, the standby buses are not only used in the event of a standby. Okay, standby buses are used all the time. They're permanently in use. All the really essential kit is on the standby buses. The name standby really refers to the fact that they have a standby power source, which is the battery. Okay, so the takeaway point is that the standby buses, all of the standby buses, are normally powered. All right. So with that in mind, the AC standby buses, because there are AC and DC standby buses, so the AC standby buses are normally powered from AC transfer bus 1. The alternate power is from the batteries through a static inverter, because obviously the DC has to be converted back to AC, so it goes through a static inverter. The services from the AC standby buses are things like the left ADIU, FMC1, McDo1, ATC1, the multi-mode receiver 1, DME1 and ADF1. So this is all essential kit, which is why it's backed up by batteries. The DC standby buses, again, same story, normally in use. The normal power source is DC bus 1, which, as we know, is power from TR1 and TR2, which in turn gets power from the transfer buses. The alternate power is from the HOTS battery bus, which is in turn powered by the batteries, which, as we know, is in turn powered by the battery chargers. These are used for the captain's displays, the upper DU, VHF COM1, NAV1, SMID1, the left stick shaker, Mach Warner 1. So again, this is the last ditch essential stuff that you need to fly your plane safely. All right, the standby power panel on the overhead panel, as it would suggest, controls the standby power source. The standby power off caption will illuminate if the AC standby bus is on power. That's on the classics only. On the NGs and the Max, it'll also illuminate if either the DC standby bus or the battery bus are unpowered. So there's more functionality with the standby power off switch on the NGs and the Max than there was on the classics. It's much more logical now. Now note that with the standby power switch in auto, this allows automatic power switching in the air and on the ground. For the classics, the automatic power switching would only occur in the air. So again, more functionality, better system in the NGs and the Max. The standby power switch itself, it's a 3-position switch, and the guard closes the switch into the auto position, which is where you really want to have it. In auto, that means that the standby normal relay and alternate relays will work as required. So if there's AC power to the aircraft, then the standby buses will be powered by the AC power. If you lose all AC power, the relays will trip and the standby buses will be powered from the batteries. That's what the auto position does. If you were to open that guard and move it across the battery, then that would manually force the standby buses, all of them, to be powered by the battery. And if for some crazy reason you wanted to switch off all standby power, you will put the switch in the middle position into the off position. There is obviously, I can't think of any operational reason why you would need to do that. It's much more for engineers than for pilots to do that. Okay, the standby power control unit. This box is only on the NG and the Max, and it controls the standby power distribution. So everything that you saw and I explained to you in the previous slide, this is where the magic happens in there. And this you'll find on the P6 panel behind the FO seat. Interesting, if you look at the rating of some of those circuit breakers, they are huge. The standby bus sections 1 and 2 are both 35 amps each. Battery bus is in 3 sections. They're each of 25 amps. And the hot battery bus and switch top battery bus are again another 25 amps each. So there's an enormous amount of power in that box there, which is why standby power is such a drain on the battery. This box, of course, has recently hit the headlines when with the Max. When it was discovered that there were potential problems with electrical bonding due to flaws that were traced to a manufacturing change back in 2019 involving fasteners and more importantly a coating on the fasteners. which could affect the electrical grounding path, causing this to malfunction. As I record this, the FAA will be issuing tomorrow a service bulletin for the necessary rectification work on this to enable the affected aircraft to be ungrounded. More details of this are on my separate video, 737 electrical bonding. That standby power unit sends the signal for the elect light on the metering panel. This again is new to the NG and the MAX, and it indicates a fault in the DC or standby power systems. This elect light will only illuminate on the ground. There's frankly nothing you can do about any of these in flight, so it doesn't want to bother you with them, but when you land, elect light will come on, and you can put this in the tech log. What the elect light is actually telling you, to find out, you'll need to go to the maintenance functions. To do that, put both selector switches into the test position and press briefly the maintenance button. Normally it will show something like that, no fault stored, which is what we like to see, but fault messages can include panel failure, interface failure, battery charging up, auxiliary battery charger up, static inverter in up, and the SPCU itself, the box we've just been talking about, in up. So as you can see, there are 6 different failures there, and they're all to do with the DC and the standby system. This is a photograph I took of one such fault, which I got. So this was the auxiliary battery charger, which was in op. The letter I after it means that the fault is intermittent and not present at this time. If you press the maintenance button a second time, it'll show any subsequent messages in case there's more than one fault simultaneously. If you press and hold the maintenance button for 3 seconds, that will clear any faults from memory. So please don't do that if you're not an engineer, because otherwise you'll wipe the evidence trail for the engineers to do the troubleshooting. Alright, quick word about DC voltages and where they're measured at. I've already mentioned the TR1s are measured at the DC buses, but the standby power is actually measured at the DC standby bus. I guess that's logical for the DC voltage. The battery bus is measured at the battery bus, and BAT is the hot battery bus. TR3 unusually is measured actually at TR3, because obviously the battery buses are reserved for measuring TRs 1 and 2. Normal battery voltage range is 22 to 30 volts, but can be up to 33 volts during pulse mode charging. And a top tip for you: don't leave the DC meter selector at the battery position on an unpowered aircraft, because doing the indication for that draws some current and it'll eventually drain the battery. So leave it anywhere other than battery if you can. The Jenny Diagnostics panel, we covered this in great detail on the AC video, but I'm just going to very briefly show you the DC section of this. And it's here, there. So those top left 6 lights show which of the DC and standby buses are powered. Now these are normally unlit, even if the particular DC or standby buses are powered, to avoid distraction on the flight deck, because last thing you want on a night flight are these things glaring out at you. So use the indicate test button, which I've shown there at the bottom. If you hold that to indicate, then those whichever lights are powered will illuminate. Unfortunately, I didn't get the photo with me holding it in the indicate position, because when I took the photo, I was more interested in the AC side, the Jenny 1 and 2 trip off. But anyway, for more details about the rest of that panel, then go back to the AC video. All right, on to circuit breakers. A note from the QRH, very important this. In flight, reset of a trip circuit breaker is not recommended unless directed by a non-normal checklist. However, a trip circuit breaker may be reset once after a short cooling period, and they suggest 2 minutes, if in the judgment of the captain the situation resulting from the circuit breaker trip has a significant adverse effect on safety. On the ground, flight crew reset of a trip circuit breaker should only be done after maintenance has determined that it's safe to reset the circuit breaker. Flight crew cycling, i.e. pulling and resetting of a circuit breaker to clear a non-normal condition, is not recommended unless directed by a non-normal checklist. Now, I absolutely echo and endorse everything that's been said there. I think you really want to have a serious think before resetting a circuit breaker which has tripped without knowing why it has done so. In flight, it really depends, I guess, which circuit breaker it was, but my gut reaction is if a circuit breaker trips, leave it tripped until you've consulted with an engineer. You really don't know what could be going on behind there, and of course worst case scenario is that if you do reset it, then something overheats, causes a fire, and then you're in a whole world of pain. So if you can live without the trip system, please do so. I would say, and this is probably news to any Airbus pilots, where resetting circuit breakers or circuit breaker resets are a way of life on the Airbus. There's a whole section of the Airbus QRH devoted to this. This is not the case with the 737, and resets to clear conditions are actually a very rare occurrence. The photo, incidentally, I thought you'd like to see rather than a regular picture of a CB panel. This was open for maintenance to get access to the things behind the circuit breakers. Quite interesting to see it. I thought you'd like that. The circuit breaker locations, they're usually in these the places indicated on this chart here. These are the standard locations on the NG. The other series are very similar. In some cases, the System 1 circuit breakers are on the P18 panel and the System 2s are on the P6 panel. That's particularly the case with P18-2 and P6-1. For instance, you've got COM1 and SMID1 on 18.2 and COM2 and SMID2 on 6.1. You obviously don't need to remember where these are. Take it nice and slow and you know, just read the caption above. One way of remembering which is the P18 panel and which is the P6 panel. The P18 panel's behind the captain. That's because the captain's paid 3 times more than the FO. I wish. There are circuit breakers in other places on the aircraft other than the P6 and the P18 panels. And I've shown photographs of some of them here. So top right, we've got the galley circuit breakers. Bottom right, these are near the rudder pedal adjuster, and these are the circuit breaker lights for well, on the left hand side it's the captain's panel lighting and centre panel lighting. By the first officer's rudder pedal adjustment, it's the first officer's panel lighting. The circuit breaker just hidden there from memory is for the MCP lighting, I think. And on the central electric pedestal, you've got the lights. The bottom right of that are the circuit breakers for the lighting on that as well. And of course the E&E bay, which is thick with circuit breakers, but obviously you as crew wouldn't normally go anywhere near those. Alright, so let's look at the two different types of circuit breaker collars, and it may come as a surprise to folk that there are two types. The first type are the collars on pulled circuit breakers. So this is for things which are either permanently or temporarily inoperative. So if you look down at the bottom right there for at the printer with the red collared circuit breaker, that collar is holding that circuit breaker in the out position. So that means that there is no power going to, in this case, the printer. That's because that system is inoperative. Now it might be inoperative either because the system is ADD'd, you know, there's a fault on it which so it's temporarily inop, or it might have been disabled by your airline or maintenance organization, or it might not have been fitted at Seattle. It could be any one of those reasons. So that's a collar around a pulled circuit breaker. Now the other type of circuit breaker are identification collars. Now these circuit breakers, and you can see examples of them here. The green one is for the CVR, and the orange one's up at the top of for the Mac trim system. These are absolutely not pulled. These circuit breakers are in, the circuit is live, but the collars are on there so to enable you to find them easily, find them quickly and easily. So the green one obviously is for crew use after an incident. The orange collars for the Mac trim system, I presume, are for engineering use. What that use is, I don't know. I'm not an engineer. But presumably there is a good reason why they're ID'd. The three white pieces of tape, that was part of my pre-flight preparation before an airworthiness check flight. These were just for me to mark these particular circuit breakers which I knew I would need to pull in flight to test those particular systems. So I just ripped off pieces of tape and put them on them so I could find them quickly in flight. And so that's my my Mickey Mouse form of identification collars for circuit breakers. Simple but effective. And finally, color coding. Now there are, as you can see in the photographs, a whole range of colors for circuit breaker collars, and I, for one, have not yet managed to identify a universally standard system for color coding. There may be one. If so, I don't know what it is. But I do know that individual airlines have got their own systems. I don't think that they are standardized across all the airlines of the world, though. Now, one airline, and I just quote this as an example, uses black for permanently inoperative systems, like the on the long photograph at the bottom, there's something inop there, and that's got a black collar around it. It uses yellow for temporarily inop systems, so these defer defects, like again in this case HF1 on the photo below, and red for crew use, so that they're things like the FDR or the CVR. But as you can see up at the top center picture, there's a photo of a CVR with the green collar. The Mac trims we saw from the previous slide has got an orange collar with that particular airline, and I've found examples in my library of white collars, red collars, and a sort of cream coloured collar on the stick shaker there. I've even found photos of tie wraps being used as collars, and this is not standard practice. This is not as decreed in the maintenance manual. So tie wraps, if you see them, they shouldn't be used. That is it from me for circuit breakers, for DC, and for electrics. As ever, if you enjoyed the video, if you found it useful, please give it a like and subscribe to my channel. Thank you very much.